in the beginning of our unit on talking about math and calculations and how you know about how to measure something. So one of the first things we want to talk about is dead babies, which nobody wants dead babies. And the way that we can avoid this is by making sure that we always put zeros in front of decimals if it's a really tiny number. So there's no place on your notes to fill this in, but if you want to make a note about it, you're welcome to. Just a quick little history here. Years ago, there was this, a large number of babies that were in the hospital that were dying because they were getting the wrong dosage of medicine. It was heparin, which is a blood thinner. And the doctors would write the prescriptions and they'd say, hey, you know, every so often you need to give them 0.5 cc's, something like that. Well, by the time they got this copy of a copy of a copy, or maybe it was the doctor's handwriting, the nurses, this happened quite a bit, they'd look at that and what do you think they gave them instead of 0.5? 5. So there was that overdosage, and so a lot of babies died because that was too much for a baby to be able to get. So because of that, the way we are going to solve that is that we are going to say that whenever you have a small number like that, get into the habit of always putting a 0 in front of it. And so we just call that the dead baby rule because nobody wants dead babies. You guys go save those children. So there's our first little lesson about some numbers. The next thing we want to talk about, and you'll notice on your notes that you have a little spot there for accuracy and precision. So it's up to you guys how you want to fill that in, but we want to make sure that we know the difference between those two. Accuracy is how close a measured value is to the accepted value. How close measured value is to accepted value. So if I told you the lifespan of a squirrel is 9 years, is that accurate? I have no idea, to be quite honest, because I do not know the life expectancy of a squirrel. So in order to know how accurate something is, there's something important that you need to know, and that would be the actual or real value. So in order to be able to test the accuracy, you need to know the real value of something. So for example, if we're talking about gold if it has a density of 19.3 grams per cubic centimeter, yeah, that's pretty accurate. That is the known density of gold. So you have to know the actual value. The other term that we want to look at is precision, and that has to do with how close a series of measurements are to one another. How close a series of measurements are to one another. And this has a large amount to do with the instrument that is being used, the lab equipment that is being used. So if you guys wanted to measure the volume of a liquid, think about that word there, you want to measure the volume. What's the name of this thing right here? Right here is a graduated cylinder, and this one is a beaker. So you guys might have played around with some of these things a little bit. This is really just more of a storage container used for maybe mixing some things. It tells you some rough ideas of some values, but our graduated cylinder is incremented a lot more. It's got a lot closer values, greater increments. So therefore, this would give you a greater precision. So this is what you would use for your volume measurement. Let's go back to an example of accuracy, because we've all played darts at one point in our lives. If you wanted to be accurate in playing darts, what would you shoot for? The bullseye, right? That is the real value. That's what you're going for in darts. So if I sat here and I threw those 3 darts and every single one of those hit that bullseye, am I very accurate? Absolutely. Am I very precise? Absolutely. I did great. What if I take those 3 darts and I'm shooting for that bullseye and every single one of them hit the foot of a tardy student? Am I very accurate? No, I really wasn't going for that, right? I was going for the bullseye. But was I very precise? Yeah, obviously somehow my arm just, I'm very precise because I always shot it in the same spot, but that's not what I was intending. Okay, so those are our examples there. Then we get to something known as significant figures. And I will tell you right up front, Nobody goes home and says, yeah, I get to study significant figures. This is awesome. Nobody loves significant figures, but it's important for us to learn. So I think there's a place for you to write this down. Significant figures are the numbers in a measurement that include all of the digits that are known plus an estimated digit, or the last digit that is estimated. Numbers in a measurement that include all of the digits that are known plus a last digit that is estimated. So for example, I've got this pencil here, and I want to measure the length of the pencil. It doesn't tell me. Let's pretend this is centimeters. It's a really tiny pencil. So here I have this ruler that I'm using. I definitely know that this pencil is greater than 2 centimeters, and I very confidently know it is less than 3 centimeters. So this value right here, yeah, I'm very confident of that. I know it's going to be a 2. I also know, I count 1, 2, 3, 4, 5, I know it's greater than 2.5, but it's less than 2.6. Again, I'm really confident about that number right there. But then this last little one, I don't see any other little lines in there. There's no other little incrementation there. So what I have to do is I have to guess or make an estimate as to what it would be. And I notice it looks like it's about halfway in between. So I'm going to based on that, I'm going to call it a 5 right there. So that last digit was my estimated one. So all of these digits in this measurement, 2.55, are significant figures. In other words, I've got 3 significant figures in this one example that I have here based on being able to use this piece of equipment to measure it with. If I go down here and I use this piece of equipment, all I really know, it's greater than 2 and it's less than 3. Yeah, I can say that with confidence, but that's about it. I can't say anything else. I have to just guess or estimate this last little bit, and I'm going to call it 0.5. So in this case, there are only 2 significant figures. And I'm going to stop this for a second and do a little demo. Okay, so now we look at this man right here, and this is not just this last Olympics that we had, but the 4 years before that. And I don't know if you guys remember, what did he win his first, I think it was his first race, but what did he win by? 1/100th of a second. Well, had he had that exact race in 1971, he wouldn't have won. They would have called a tie, right? Because prior to 1972, the Olympic events were only measured to tenths of seconds. So now, because we can measure it, we have greater precision, greater instruments, we can measure it to hundredths of seconds, and he gets another gold thing hanging around his neck. Okay, so let's look at some rules for counting significant figures. You have these listed on your sheet. I went ahead and put a couple examples on this slide, but there's really not a need for you guys to write these examples down. We're going to go through a bunch of them. First few are pretty easy. People don't typically have problems with the non-zeros. It's the zeros that start throwing people. So the first one just says, all non-zero numbers are significant. Yep, that's true. I look and I just count the digits. There's 3 of them. There's 3 of them. Those are usually pretty straightforward for people. That's just counting the number of significant figures. If you have sandwich zeros, in other words, you've got a non-zero number on each side of that 0, then those sandwich zeros are also significant. So these are also pretty easy for people to count. And you can just see we have 3, 5, 5. So that's our rule there. Now we get to leading and trailing zeros. Leading zeros are never significant, because think about what a leading zero means. It means that you've got a really small number, and those zeros right there, all they are placeholders. That's all they are. Let's say I said that, hey, it's 8 meters for me to go walk over to my friend's classroom if I wanted to do that. 8 meters. Well, how far is that in kilometers? How many meters are in a kilometer? 1,000. So think about what you do. It ends up being 0.008, right? Everybody agree on that? So in this case right here, you guys can easily look at that and say, yeah, there's one significant figure. there's still just one significant figure. Just because I put it into kilometers instead of meters, that doesn't suddenly give it more significance or importance. So these leading zeros are going to be insignificant. They're never significant. Okay, number 4 says that trailing zeros are significant if there's a decimal point that's present. So these first couple examples that we have here, we see that we do have a decimal point present, meaning that those are measured values. Yesterday when I showed you guys something on the balances, on the balance back there, I talked about how it's measured out to the hundredths place. Here, this would be an example where it's measured out to the tenths place, but that is a measured value. You could just as easily put something on that balance and it measures as 67.4, right? So that is a significant value. In this example here, we see that there is no decimal point, so therefore these zeros, yeah, they're trailing zeros, but because that decimal point's not present, then they are not significant. Let me go back to my conversion type of example. Let's say I had, let's say we've got something that's 5 kilometers, and I want to figure out how many meters is that. Well, that's just going to be 5,000 meters. So again, here I've got one significant figure. I still have one significant figure. These guys aren't significant. They don't have anything to do with creating a greater precision of that value. All I did was convert from one unit to another. Okay? And then the last one is really the easiest of all, and it's just that exact numbers of significant figures, exact numbers have as many significant figures as are needed. So you never use those in your calculations to try and determine something. If I were to use an example, let's see, 1, 2, 3, it looks like we have exactly 27 students in here. In other words, 27.000000000. There's no fraction of students hanging around that I see. You guys are a count. So because of that, it's unlimited. It's an infinite number of significant figures. Okay, so with that in mind, there's your list or your rules for counting significant figures again. It's good to know those rules, but sometimes people like quick, easy shortcuts on how to go about thinking about it. And for that, we can use our geography. So quick little geography lesson here. What is this ocean? Pacific. What's this one? Atlantic. So there we go. We've got the Pacific and Atlantic Oceans. Think about those as saying something about the decimal point. The decimal point can be present or it can be absent. And so that's what you have to think about. Is that decimal point present or absent? Regardless, and it's up to you if you want to jot this one little sentence down, because this is the helpful part if you try and use this method for thinking about it. That regardless of which direction you start with, you always start with your first non-zero number. Always start with your first non-zero number and keep counting till you fall off. And keep counting until you fall off. Always start with your first non-zero number and keep counting until you fall off. But you have to think about which direction you're going to start counting from. So that's where our Pacific and Atlantic comes in. So I'm going to jump ahead. If I can find out what I just did with, there we go. Okay, you don't have these exact numbers. Don't worry about writing these examples down. You've got plenty of examples. But in this first one, we look at this. First thing you ask yourself, is that decimal present or absent? It's present. So I'm going to start over here at my Pacific, and this is hard to show on video, but this is where I'm starting from. So I'm starting over here at the Pacific Ocean because that decimal point's present. I'm always, always, always going to start at my first non-zero number. So what number is that going to be? The 3. And I keep counting until I fall off. So how many significant figures do you have? 4 significant figures in that example. Okay, next one. Hey, is that decimal point present or absent? It is absent, so I'm going to run over here to the Atlantic, and I'm going to start at my first non-zero number. And so when I start there and keep counting until I fall off, how many sig figs do you have? 4. Okay, so you know what I meant to do? Let's go with this one. Look back at your list of rules. Which rule does this one entail? The first one, this is leading zeros are never significant. And so this one is trailing zeros are significant when there's a decimal point, which means they're not significant if there's not a decimal point. So you can relate these back to the rules that we just learned. A lot of people liked the shortcut of the little geography lesson here. Some just use the rules. It's up to you guys. Okay, this example, decimal points present. So you run over here to the Pacific. You start at your first non-zero number. Keep counting till you fall off, so count those up. How many? 8. So there we go. And again, your trailing zero is significant because there's a decimal point that's present. Okay, so now we have, I'm going to make it be the class's turn to fill these in, and I'm just going to turn this back on when they're done. Okay, so we just filled in all of these values because they are so incredibly smart, they figured them all out. Okay, oh, actually, let me just point out, this one right here, that has scientific notation in it, and I did mention that it just needs to be the coefficient in front that you look at. Okay, so now what we want to do is we want to think about rounding, and with rounding, these rules you guys are probably already familiar with. It's probably what you would do naturally, is if it's 5 or greater, you would raise it up to the next number, and if it's less than that, then you leave it alone. So we're going to do that with this value right here that's given to us, and I'm going to write it really big. So there we go. Now what we want to do, if we want to take this value and round it to 2 significant figures, what you're going to do is you're going to cover up everything except the last 3 significant figures. So I see a 21.4. That's what I'm not covering up. All this other stuff, I don't care. I'm not going to start back here and round up as needed. I'm just going to cover up everything except the 21.4. So when I round 21.4 to 2 significant figures, what do you get? 21. Does it matter if you write it that way or that way? Nope. Either one's good. But could you write it that way? No, because that would be 3 sig figs. So that is not correct. Okay, which takes us actually to this next one. Let's look at our 3 sig figs. Again, you just hide everything except now 4 significant figures. So what I'm showing here is the 21.40. So when you round that to 3 sig figs, what are you going to write? 21.4. And this is just one of the many reasons I think that people hate sig figs. It's very tempting to look at something like this and think 21. 21, that's pretty much the same as 21.0, 21. It doesn't matter, they're the same number. But that 21.0 is saying that, yes, I've measured it to this degree of precision. I know that this is the correct measured value. When actually we see in this example, it's not. It's 21.4, not 21.0. So that's where the difficulties come in. Okay, next one. 4 significant figures. What are you going to call that? 21.41. Okay. Now I'm going to cover up everything but 6 of these guys. So I see 21.4096. Rounding it to 5, it becomes 0.410. Okay. So that 6 rounded the 9 up, which rounded that 1 up. Okay, 6 significant figures. That becomes, wait, I can't count. Hold on. 1, 2, 3, 4, 5, 6, 7. So I'm showing everything up to the 5. If I round that to 6 significant figures, it becomes 21.4097. Then finally, to 7 significant figures, 21.40965. No, because in this case, we've got, this is what we're showing, right? I've got my hand, which you can't really see on the video, but my hand's covering that 3. So I'm looking at this and I'm thinking, okay, the way this is going to work is that this 5 rounds this up to a 7. Okay. Let's go ahead and see now how we go about doing some calculations with significant figures. And I'm going to rewrite these or reword them because I don't really care for the way it's phrased. But we have two different sets of rules that we're going to use. We're going to have a set of rules for multiplication and division, and we're going to have a set of rules for addition and subtraction, which is what this is telling us. But my set of rules for multiplication and division is to round to least number least number Sig Figs in given problem. Round to least number of Sig Figs in the given problem. So if I were to start this off, let's look at that first example that we have. And it's all been plugged in for you. So you have this something times something times something divided by something divided by something. And you plug that in, and your calculator spits out this number for you. So that's what's in your calculator. Do you really want to write all that stuff down? Because your calculator is not as smart as you guys are. You might think it is, but it's not. You now need to round this to the correct number of significant figures. So based on this rule, think about it for a second, and you should be looking at this part right here. What is the least number of significant figures in your problem? Don't say it, but show me with your fingers. Seeing lots of right answers and some not so right answers. Okay? Anybody feeling really confident? Okay, green shirt. Sorry, I don't know names yet. What's your name? Tim. What do you think? I think it is 3 as well, because Tim's looking at this one right here, and he says 0.00290. That is 3 significant figures. That is our winner. Here we've got 4. Here we've got 4. Here we've got 5. Here we've got 5. 3 is the smallest. So because of that, we now have to take this value and round it to 3 significant figures, which becomes 0.0. Are any of those significant yet? No, those are just the placeholders. I'm just throwing those down. Now tell me, what are the 3 significant figures? 170. Okay, so that's our right answer. Okay, good. Let's go ahead and, let me fill in a new definition for the addition subtraction before I go on to the next example. Instead of the way it's phrased here, I think I'm going to say that you round to least number digits past decimal. Round to least number of digits past the decimal. And we'll get to one of those examples after we do one more of the multiplication division. So right up there we see we're multiplying 2 values together. We get this big long answer on our calculator, but we know that we're going to round that to how many sig figs? 3. So when we round that, who thinks they know confidently what the answer is rounded to 3 sig figs? Okay. Okay. I'm hearing a couple different things. 265, and then I did hear 00. What if you just said, let's say I owe you $26,464. Ooh, but I don't have the exact change on me right now, so I'm just going to round it to 3 sig figs and just give you $265. Would you be okay with that? Chances are you wouldn't, but if I said I'm going to give you $26,500, then you'd probably be okay with that, because you have to remember to add in those insignificant zeros. This was a situation, and that's a real common mistake, that people forget to add in the insignificant zeros. Okay, now we're getting to our addition and subtraction. Remember our rules. I don't really care that there's 4 sig figs there, 5 sig figs there. That doesn't have any meaning for me when we have addition and subtraction. Instead, what I want to look at is the number of digits past the decimal. So in this first one, how many digits past the decimal are you saying? 2. Right, 2 here, 1 here. This is going to be our winner, right? and then 4 and 2. So the fact that there's one digit past decimal, that's going to be the winner. That's what decides how we round this. So we're going to round it to 102.06.5. Okay, so that's what we've got there. One more. How many digits past the decimal are you going to round this to? 2. So that becomes 42.36. And last little bit of stuff that we have to do now is we're going to go ahead and do some stuff with scientific notation. I am checking the time, 5th period. We're doing okay. So with scientific notation, you guys have done this in the past. There's this whole list of blah, blah, blah rules that you guys can read through. The main thing to remember is that your coefficient, whatever that number in front of the times 10 to the is, that coefficient needs to be a number between 1 and less than 10. So that's what you need to remember. It needs to be between 1 and less than 10. So let's start with this first example. Make that be a number between 1 and less than 10. 6.74. There's our coefficient. Scientific notation, so we know it's going to be times 10 to the something. Well, in order to do that, how many places did you have to move your decimal? 8. Well, let's go back and think to ourselves, is this number right here a really, really big number or a really, really small number? It's really small. So what does that tell you about the sign of your exponent? It needs to be negative. That's the easiest way to do it. Some people like to memorize, well, when you move in that direction or you move in this direction, you get positives or negatives. But you have to think about which direction you're heading as well. So I think it's just the easiest thing to do is to think about whether or not something is a really large or a really small number, whether that exponent's positive or negative. Okay, I'm not going to spend too much time on something like this, but is this written correctly in scientific notation? Because not between 1 and less than 10. So what you guys could do with something like this is just one idea. There's a couple different ways to do this, but if you wanted to make sure you were able to answer something like this correctly, change it ever so quickly to regular notation. So this says -9, meaning you're going to take that decimal and move it which way? Right, that way make it really small. You're going to make it smaller. So you're going to move it left. So we're moving, by doing that, I'm going to go ahead and write this out. You probably wouldn't need to, but I'm going to add 9 zeros in there, plus the original 3 zeros that are in there, and then 3, 7, 8. So now when you change that to regular scientific notation, which is going to be 3.78, because now that number is between 1 and less than 10, how many places did we have to move that decimal? -13. So those 12 zeros plus that 3 as well. Oops, I should put a 10 in there, shouldn't I? Okay. Last little thing, and for this, I am not going to teach you guys the math part of things. That's what you guys do in your math class. But as far as when you multiply numbers in scientific notation, the exponents add, that sort of thing, you're welcome to use that. That's good knowledge to have. But in chemistry, and I can't reach it from here. I know I've got one somewhere. In chemistry, oh, I can't reach it. This is very anticlimactic. We use calculators. Everybody take a second and grab your calculator if you happen to have it. Okay, so my main goal is to make sure that you guys know how to plug this into your calculator correctly, because that's what we do in chemistry classes. We rely on our calculators, which is really a good thing, but you should always be able to look at something and make sure it's a reasonable number and that you plugged it in correctly. So if what we want to do in this first example is multiply these two values together, well, the first one, it says 9.6 times 10 to the -4th. I am not able to install my little thing that shows the calculator online on the screen yet, so I just kind of copied this one down. But what we want to plug in first, this is what we want to plug in. So the way we would do that is we would type in the 9, the decimal, and the 6. It's easy enough. But never do you punch in the times button or the 10 button. So the next thing you're going to do is you're going to hit this key right here. It's yellow on a lot of your calculators. It's that second function key in the upper left-hand corner. So you punch that in, which takes it to the things that are above the buttons, which the next one you're going to go to is that comma, because what you want is the EE, which is your scientific notation, your exponents. So 9.6, second function, EE. What you've just done is you've said 9.6 times 10 to the, that's what that is. And so the next thing you have to do is just plug in negative and 4. Make sure you hit the negative and not the minus, because that's another mistake that happens. So now once you've done that, just get into the habit of always having your times 10 to the be those two buttons, and that's all there is to it. If you try doing it some other ways, you'll probably get your answer correct as far as the coefficient goes, but what's going to happen is your exponent is going to be off by an order of magnitude of some sort by doing that. Yeah, so the buttons over on the right-hand side, here's, and I've been guilty of making this mistake when in a hurry or something. Here's the minus, but what you need to make sure you push is the negative right there. Okay, and so let's go ahead and just punch the rest of it in, and what do you guys get whenever you get to that point? Okay, so I think I'm hearing the right things. 2.4, is that what we said? Times 10 to the negative 8th. Beautiful. And in fact, and I'm going to walk around and check you guys, but this is the end of the video. I'm going to go ahead and plug this in, and I'm going to check calculators in the room. Bye-bye. You did great with your first lesson.